Good afternoon, ladies and gentlemen. I would like to give a warm welcome to Marwan Tammam from Google. You may start. Thank you.
All right, thanks. So hello, everyone. Thanks all for joining. Today's talk is going to be about executing cohorts in bulk using FHIRPath. So a little bit about myself. My name is Marwan. I'm a software engineer at Google. I've been working with the Google Cloud Healthcare API team for about 3 years now. Most of my work have been around developing features as part of the Cloud Healthcare API. Most of them related to the FHIR API. And one of the latest projects that I've worked on is executing cohorts, which today's topic is going to be about. So the agenda for today, first we're going to discuss a bit what's the problem we're trying to solve here. And we will go through some of the existing solutions as part of either the FHIR spec or other implementation guides. And then we'll define what it means by a cohort definition and what it means to execute a cohort. Next, we'll touch a bit on FHIRPath, since this is basically the tool we're using here for our solution. And we'll discuss why and how we are using it for the definition of cohorts. And next, we'll see how to use FHIRPath to define a cohort and how we can execute it at scale. So first, what are we trying to achieve here? So we're trying to define complex cohorts. So a cohort is basically a group of FHIR resources that meet specific criteria. So you may need to define a cohort for different use cases. This can be for research, analysis, clinical trials, and others. So a cohort can be defined in terms of eligibility criteria. So say, for example, you're interested in patients between a specific age range. A cohort can also be defined in terms of inclusion and exclusion criteria. So say, here's an example for a simple cohort. So the green part here is an inclusion criteria. So we're interested in patients with this BMI range. And the red part is basically people who did not achieve weight loss without surgery. So you can think about this in terms of excluding patients who achieved weight loss with non-surgical methods. So this is the first part of our goal here. The second part is after we defined our cohort, we want to actually execute this cohort, like I said, at scale, which means pulling up all the resources that meet these criteria, and then send it to a downstream use case later on. So this is a figure that I pulled up from the Vulkan implementation guide, just to show some additional examples of these criteria that can be used to define a cohort. So the red figures here are the FHIR resources, and the ones in gray are examples of criteria, and the arrows how they can map, how you can map these criteria to the FHIR resource. So for example, you can have criteria based on patient demographics, birth date or gender. These can be captured in a patient resource. You can have criteria based on visits to a hospital, for example, the visit date and so on. You can have criteria based on diagnosis, what was the patient diagnosed with, lab tests, procedures, medications, and so on. So some of the use cases why you might need to define a cohort. So one example is basically defining a cohort in order to train an ML model. So say, for example, you want to study Alzheimer's disease for patients over 50. So in this case, you're only interested in a subset of the patients or the FHIR resources. So you can define a cohort for this specific use case to train, for example, your model. Another use case, which is also related to the first one, like usually when someone trains and a model wants to get like consistent results. So say, for example, you defined your cohort and then like you fine-tuned your model and you want to train it again on the same set of data. Say you didn't store it, so you want to run a cohort and get the same data again. So you might need to you might need to be able to query historical versions, because like some updates may happen on the FHIR store. So you may need to like specify a specific timestamp and say, I want this cohort at this particular time. Other use cases can be like cost saving. So say you don't want to store everything in your FHIR store, you want to archive some of the old data, or you want to move just like a subset of your data to another store instead of like storing everything in one single store. Other use cases can be like for validation and testing. So usually if you want to do testing or validation, you want to only test on the subset of the data that you have. So this can also be a use case for defining a cohort. So we first looked at like some of the existing solutions in the FHIR spec or implementation guides. And one of the solutions that may come up to mind is FHIR bulk export. So this is like a bulk operation which allows you like to export resources from your store. The problem here is like there's a limited set of parameters for bulk export. So you can do things like there's a sense parameter, there's a type parameter, which allows you like to filter on the resource types. I know there's also like the type filter parameter, which is like an experimental one, which allows you to specify like some sort of search query, but the problem is still like it's not fully powerful. So there are many use cases where you're still limited by this. And we'll also discuss later why we decided to go with FHIRPath instead of like something like FHIR search, query language, or others. But yeah, mainly FHIR bulk export is not very flexible in terms of like the offering like powerful queries that you are able to run. A second solution is, for example, doing a FHIR search. But the main problem here is FHIR search is not designed to like get data at scale. So it's like a synchronous API call, and usually servers will limit the page size. So like the number of results you get in your search response in order to like fit the response size. So the third thing we thought about is what if we built like a wrapper around FHIR search? So basically this wrapper will like go through the pages of your search result until it collects all the data that matches the search query. And we can also like try to run these searches in parallel instead of like waiting for the first call to end and then like make another call and so on. So what we tried here is basically if you have like any search query, you can try to add like two parameters to it, a count parameter, so we only want a count of 1. And you can also add an additional sort parameter, sorted by the last updated. One time you will sort ascendingly and one time descendingly. So this way you get like the first and last result. Now you can divide, so now you have a late range. You can divide it into like n segments. So n here can be like, for example, the number of threads. And you can try to fetch the results for each of these segments in parallel. So each segment will have these additional search parameters, last updated greater than and less than for the equivalent segment that you're trying to get the results for. But still, the problem is like most search backends, or at least our implementation is not designed, like it's not optimized to return such a large number of results. So here we're speaking in the scale of like millions of or billions of resources in a store. And also it's not common for the resources to be uniformly distributed according to the last updated field, because you would assume like there are like some peak hours, for example, in the hospital where you would get like a large number of resources. So yeah, it's not like uniformly distributed across these date ranges, which like you may end up having like 1 or 2 segments having like the most number of results. So you wouldn't gain much by doing this kind of parallelism. And also, like we said, we wanted to be able to reproduce results. So once you introduce updates to the store and say you want to fetch results at a past timestamp, this can make things pretty much more complicated. So we thought about like defining a new async batch operation, which will be mainly designed for defining and executing cohorts, and it will run a batch operation similar to FHIR export, and will return the results or send them to another like pipeline. So we had like 2 main requirements. So we wanted this operation to be able to scale to a large number of resources, and we wanted to be as flexible as possible and to be able to run very complex queries so that it can fit most of the cohort use cases we've seen. So like we mentioned, a cohort is basically just a group of resources that meet specific criteria. So you can define a cohort as like just in text, like the examples we've seen before. For example, patients with Alzheimer's disease. It can also be expressed as a FHIR search query. So you can take this text and try to map it to like the equivalent FHIR search query. You can also define it as a like FHIR bulk export request, assuming the like, parameters fit what you're trying to represent. You can also do this as a SQL query, assuming you have your data in a SQL database already. Or you can use FHIRPath, which is what we chose in this case, or others as well. So why did we choose FHIRPath? So FHIRPath is defined by the FHIR spec, and it's specifically designed in a very good way that works very well with FHIR resources. So it allows us to easily navigate and extract data. It's also used in several places. So as opposed to FHIR search query language, for example, where it's mainly used for search, FHIRPath is used in other places like profile validation, search parameter path, FHIRPath patch, and so on. It's also much more powerful than FHIR query language, and there is like so much more you can express in FHIRPath. It's also not too verbose like SQL or CQL, for example. So it makes writing these cohorts much easier. And the last thing, it's extensible in a way that you can define custom functions. So there are already like implementations of FHIRPath that define their own custom functions. And we also, like, if you've seen the SQL and FHIR v2, for example, they define like the get resource key. So it's not uncommon for implementations to define custom FHIRPath functions. So this is another example of a cohort definition. It's taken from the evidence-based medicine implementation guide. So the details here are not very important. It's just like a cohort definition for patients with non-fatal stroke. So it has an inclusion criteria here, which is basically patients who had a stroke, and the exclusion criteria is any like death event. So this is like just a demonstration of how you can represent this using SQL and FHIR. So you select from the condition table, and you filter, then join with the patient table, and so on. We're not very interested here in this because we're assuming the data exists in a FHIR store as opposed to a SQL database, but just to show like how this compares to the other options. So as you can see, the same cohort definition can be expressed like this in FHIR search or FHIRPath. So you can see here it's already much more compact compared to SQL and FHIR. So I'll not go into much details here about the query, but basically like it's like doing the same thing. For example, the FHIRPath, we're getting the condition, and then filtering according to the code for the stroke, and then resolving the subject, and then like doing wear on the deceased field. So also like this is not very accurate because usually you would like also need to check if the deceased date time is not set, but just for demonstration here. So like I mentioned before, FHIRPath is much more powerful than FHIR search. So a few examples here. So a simple example is like FHIR search, you cannot actually query based on or joins of different or unrelated elements. So for example, you can't say, I want to search for patients with a given name or last name equal John. You can say given name equals John or Bob, but you can't do this on like two different elements. There are some ways you can do this, but you need to like define composite search parameters. Other ways you need actually to issue multiple requests in order to achieve such thing. You cannot also do complex logic, which FHIRPath enables you to do. So things like union, intersection, string manipulation, arithmetic, and so on. Yeah, also like the more the query becomes more complicated, it becomes like much harder to write using FHIR search, or at least this was my experience. So now that we have decided to use FHIRPath for defining cohorts, so why not just accept any FHIRPath expression? So the reason is FHIRPath is not just built to operate on FHIR resources. So any FHIR search query actually has a meaning, but in FHIRPath you can do things, for example, 1 + 1 is a valid like FHIRPath expression, but it doesn't have any real meaning in our context here of defining cohorts. So what we decided to do is like to put some constraints on what kind of expressions you are allowed to pass to the request. So the first constraint is the expression must begin with a valid resource type, or if you want this expression to apply to any resource type, you can start with the base type, which is resource. The second constraint is the expression needs to evaluate to either a Boolean value. So if it evaluates to true, then the base resource, like the resource we're evaluating on, will be matched if it evaluates to true, and if false, then we skip it. Or the expression can evaluate to a collection of FHIR resources. So the reason we put this second option instead of just Boolean is because once you start to introduce the resolve function of FHIRPath, resolve can actually give you multiple FHIR resources. So if you're just constraining everything to a Boolean, then your expression can only end up with like at most one result. But if you allow a collection of resources, then you can actually use resolve in a much more effective way. So these are some examples of like supported expressions according to the constraint we set in the previous slide. So a patient, this is a valid expression because it can return one resource or none. The second expression here will return a Boolean, so it's valid. This can return a collection assuming performer resolves to something. Some examples of unsupported expressions can be like string, literal, foo, or a patient.name. Although this starts with a valid resource type, but the expression doesn't evaluate to either a Boolean or a resource. So now let's look at the steps we can do to execute a cohort definition. So by the way, what I mean by executing a cohort is not actually executing expression. Executing a cohort means, in this context, like executing the whole cohort definition on the store and then getting the whole like result set in the end. So we start by initializing an empty set of results, which we will return in the end. And then we will read the relevant FHIR resources from the FHIR store. For each resource R, we will use our FHIRPath engine to evaluate the expression on R. If the expression evaluated to true, we add R to our result set. Otherwise, if it's a collection of resources, then we union it with S. And then we remove any duplicate resources, and then we return. So although this may seem pretty much straightforward, things can get a little bit complicated once you introduce the resolve function, because now you're not just looking at a single resource, you're looking at other resources in the store as well. So you may need to think about how you will go about resolving these. So we had mainly 3 goals, and these introduced also like 3 challenges. So I'll go through them one by one and talk about what would be like the obvious solution. So first goal is to support the resolve function. So if people are not familiar, resolve basically takes a FHIR reference and should return, like it tries to resolve this reference, and if it points to a valid resource, it should return this resource. So the obvious solution is just to have like a table with 2 columns, the resource ID and the JSON, and you can stop evaluation once you reach a resolve function, go look up this table for the reference. If you find it, return the resource, continue evaluation, and so on. Second challenge is we actually wanted also to support something which does the opposite of resolve. So something similar to rev include of search. There are actually some cohort definitions that you cannot express using resolve only. You would need the inverse of this. So if there is time at the end, I can give examples of such expressions. But yeah, in short, we wanted to support something which basically you give it a patient, for example, and you want any conditions that points to this patient. So in this case, you don't know actually the ID of these conditions. So another obvious solution here would be just to store the references in another table. So you can have the source, the target, and the field, and you can use this table to go and read like these edges in order to return the appropriate result. So the third challenge and goal is that we wanted to be able to execute cohorts on historical versions. Like we said, we wanted to be able to reproduce results even if there have been updates on the store. We want to give it a specific timestamp and return the results at this particular timestamp. So the problem here is if you like store this table, you would need to also maintain all the references or edges for each resource version, which introduces also extra cost, additional overhead when you update any resource, in case you want to duplicate all these edges for any updated resource, so you can maintain the history as well. So yeah, it didn't feel like this would scale very well with so many updates on the store. So what we thought about is basically to model the resources as a graph. But at the end of the day, these like references can be simply considered edges anyway. So the node would be like the resource itself, and any fields as it points to that's a reference would be considered an edge. So this is like just a simple example here for procedure with 2 fields pointing to 2 different practitioners. So yeah, we can model the resources as a simple graph like this. So now instead of having the resource and evaluating on it, we will construct a node structure. So the node will have an ID of the ID of the node will be the ID of the resource itself. The node will also contain the resource, JSON, and it will contain 2 lists, outgoing references and incoming references. So the outgoing references can be easily parsed from the resource itself because they're actually part of the resource. But the other challenge would be how to construct this list of incoming references. So this is like the pipeline of what we ended up with. So in summary, what this pipeline does is like it reads the resources, tries to construct this graph with incoming and outgoing references, and then it uses this graph to resolve any reference assuming the expression has a resolve function or reverse resolve or rev include or whatever it's called. And yeah, it keeps evaluation until we finish all the resources. So we can go through this pipeline. So the first step is like we read every resource from the database. Then we group them into key value pairs. So the key here will be the resource ID, and the value will be like the resource itself, for example, the JSON of the resource. Then we map the values to the node structure that we talked about. So in this case, we will only populate the outgoing references. The incoming references will be empty. So now we have a graph of outgoing edges only. The next step is for each node in this graph and for each edge or reference, we will emit a key value pair where the value will basically be an empty node. So the reason being is that, for example, if you have like resource X points to resource Y, so we will emit a node for resource Y, and since we don't have actually resource Y, it will be empty. And this node will only have an incoming edge coming from resource X. So in this case, you will have this node here. This FHIR resource will be empty. Outgoing references will also be empty. And the only thing you will have is an incoming reference from resource X, which is like the node we're processing right now. And we'll do this for all references and for all nodes. And once we have done all this, we'll have like a large list of all, like a large list of nodes with incoming references. There may, of course, be duplicates because a resource can be pointed to from multiple other resources. And now we have like the graph and the reverse graph. So we can combine all these, like we can group all these nodes according to the key, which is like the resource ID. And we keep aggregating these incoming edges. And the resource from the graph itself, we can also aggregate it to build the whole node structure. So yeah, now we have like the complete graph. We can start like evaluating our FHIRPath expression for the cohort definition. So we take each node again, we evaluate the expression on this. If you don't have any resolve or reverse resolve function, then we don't need to do anything extra. We just return, like if the expression evaluates to true, we add the resource to the result set. If not, we just skip it and process the next node. However, if it has a resolve function, we will use this graph that we have constructed to either read from the incoming references or outgoing references, and then pass it to the engine to continue evaluation, and so on. If we have another resolve, we do the same thing until we're done. So, so these are some of the things we thought about doing next. So right now, the API we've built is just accepting the FHIRPath expression as like just a string in the request. We thought about storing these FHIRPath expressions somewhere within the Firestore so that they can be easily retrievable, or you can add some metadata to these resources. So one of the options was using the view definitions of SQL and FHIR v2. So this, in the view definition, there is a where clause where it's basically just a FHIRPath expression. So one option you can do is to basically put your FHIRPath expression in this where clause. And assuming also you are, like your sync is not just like outputting like NDJSON files. If you want to send them to a SQL database, then you can actually use this view definition also to define what, like in the select fields, to define what columns you want to export as well. So in this way, you can do like both row level filtering and column level filtering if you use like view definitions. Another option for storing these core definitions is to use the group resource in R5+. So starting from R5, the group resource actually has a characteristic field where you can store an expression and there is a language field, I think, which has FHIRPath as one of the options. Another thing we wanted to do is to support access control for cohorts. So right now, for example, if you're a clinician or a researcher and running a cohort, you basically get access to everything in the store. And so if you use the consent resource or access control methods, you can like restrict access to only the resources they have, like either the patient gave consent to or they should have access to these resources. And finally, we were thinking about maintaining referential integrity. So some customers were actually asking like how we can export or execute a cohort and maintain referential integrity, which means like any resource should have like the all the references in this resource should also be exported, even though I didn't like include them in my cohort definition. So if I, for example, have a cohort definition for patients, then some customers were like, for example, asking that we export also all the references in these patient resources. So this is like something we're thinking about how to support in the future. So yeah, these are some of the resources of the things that I've talked about today. Yeah, these are my contact details. You can find me on Hova app or LinkedIn or email. And yeah, this is a recap. And yeah, that's all I have for today. And time for a Q&A.
Thank you very much for your interesting talk. Time for questions.
Thank you very much. That was very interesting. So a question that I have is that basically graph of nodes to incoming and outgoing. Do you build them on the fly, or like that's something that as the FHIR store receives new resources, you just keep building in and it's always ready, it's always warm?
Yeah, so yeah, we build them on the fly. So this pipeline is actually something similar to a MapReduce pipeline, where it does like data processing on like several machines. So we read the resources and then we divide the work across like multiple machines. So everything here is done on the fly when you run your operation. We don't store any graph internally. We'll build it once you start the operation. So yeah.
Hello, excuse me. Brian from Microsoft Research. I was just thinking back to the section where you either accepted a Boolean or a resource. Was there a reason you did that rather than just saying, well, we don't want the resource, do a .exists or a .all or .many, so fall it back to one of the FHIRPath native to turn it into a Boolean? Because if you're trying to return the resource, then from an optimization standpoint, you don't want the whole resource. You only care if it exists or not, or am I missing something?
Actually, if you want to do additional filtering on the resource, then you want the actual resource, because
isn't like looking at this graph as you go through, isn't it the end point, or is the resource that's returned from that expression what you're actually returning to the output?
So if you have, for example, let's say an observation, and let's say it has a reference field, for example, this field is repeated, and you run resolve on this field, then it may return a collection of FHIR resources, right? So if you just end up here, this collection of FHIR resources are the ones that you actually are interested in, that should be included in the result.
Okay, so it's not a where clause to say filter out to it, it's a resolve to actually find the resource to return.
Yeah,
okay.
So it doesn't actually return the base resource or the resource we started from always. Like you can end up with a completely different set of resources.
Okay, cool, done.
You start with read FHIR resources. Which ones?
Sorry?
All of them? You start with read FHIR resources.
So there can be some optimizations here. So if your expression doesn't have any resolve function and your expression just starts with patient, then you don't need to read any like resource type because there's not going to be any resolve happening. So in this case, you can optimize it by only reading the patient resources.
Does your cohort definition criteria, you had that console, right? In one of your deck slide.
This one?
The next one, the one which talks about the inclusion, exclusion.
Oh, yeah, sorry.
Yeah. So when it comes to any changes up there in the criteria, how and where you are planning to tackle, like if there are additional FHIR resources getting added through, is it some way getting driven by the patient population first and then you navigate through to resolve all the relationships and identify the list of resources, or?
So no, this is actually built to run like a specific timestamp. So like it takes the current state of the resource and it outputs the cohort definition once. So any updates that come later on will not be captured. This is actually another use case that we're thinking about is like the streaming use case, but the solution here will be completely different because like you will not do like this sort of pipeline that builds a graph. So it has to be a completely different solution if you're interested in like streaming use cases.
Thank you.
One more question. Is this FHIRPath expressive enough to have a multi-resource condition? So for example, if I want to find every patient that they had a heart attack before age of 40, so now I want the encounter date and the patient date of birth, and then I want a condition on that. Is it possible to write a query like that using this FHIRPath version that you have?
Yeah, it should be possible to write these kind of expressions. So yeah, even expressions like that span multiple resources should be possible as long as we support this resolve or reverse resolve functions. So yeah, you can jump from one resource to another and run your search criteria or whatever on the other type. So yeah, you can do all these sort of things. So actually in the example here, I think so yeah, I think this example here filters on the condition, and then when you call resolve, it does some additional filtering on the patient as well. So yeah, the example you mentioned is definitely possible. It should be like something along the lines of this one as well.
Hi, great presentation. How do you satisfy the terminology-related queries that you have, for example, the subsumes function that you have there up on screen?
So this particular, so it depends on the FHIRPath engine you're using. The FHIRPath engine we're using for this implementation doesn't actually implement this subsumes function. But again, if you if you want to support this, it goes back to how you implement your FHIRPath engine. So the FHIRPath engine is actually separate from this solution. So you can just put any FHIRPath engine in this pipeline and it would work normally. So yeah, I mean, the solution is not really dependent on FHIRPath. If you just choose to use like something completely different, like just say the FHIR search query language, you'll just like remove the FHIR engine and put this in its place. The rest of the pipeline should behave the same. So it's not really dependent on what the FHIRPath engine supports.
So you execute your FHIRPath over each resource individually rather than sort of converting it into a query that you run over a data set. Right, thank you.
no more questions? Then thank you very much for this great presentation.
Okay.